Our speaker today is Manju Menon, and she will speak on security in graphs and networks. Take it away, Manju.
Thank you. Thank you. Namaste to one and all. First of all, let me thank Sandra ma'am for giving me this opportunity. And definitely thanks to the technological world. I mean, the people from all over the globe can have the same lecture at the same time, which we couldn't believe some years ago. So thanks to the development of technology also. And this talk is titled as Security in Graphs and Networks. I know that Sandra ma'am has a book titled Graph Theory and Networks. So I sincerely hope that the participants have a basic knowledge in graph theory. So with that assumption, let me enter into the talk. So security in graphs and networks. We will discuss what is this security means about graphs and networks. Any communication network can be mapped as a graph where the nodes represent the vertices and the links between the nodes represent the edges in the graph. So many graph theoretical parameters are useful in the study of interconnection network, especially studying the reliability and efficiency of a network. Like connectivity of a graph, diameter variability, diameter vulnerability, Y diameter, and many other graph theoretical parameters play an important role while studying an interconnection network. Actually, they help us to study the reliability and efficiency of a network model. So, whenever we are dealing with security terms, I mean, if you're going through the literature, the meaning of security, you can see two definitions in the same name. One was defined by Brigham and et.al. in the discrete applied mathematics in the year 2007, and we are using the definition given in this paper. Another notion in the same name, I mean, the security itself, was defined by Cockayne et.al. in a paper titled Protection of a Graph that appeared in Utilitas Mathematica in the year 2005. Both are different, and please note that the security in this lecture that we are dealing with is the definition given in this paper. That means Brigham and SP identity, security in graphs, that appeared in discrete applied mathematics in the year 2007. So let us move on to some basic definitions that is needed in this talk. The open neighborhood and closed neighborhood of a vertex. Whenever we are dealing with a singleton vertex, the open neighborhood of a vertex is simply the neighbors of that vertex. That is denoted as n of open neighborhood of x. That is a set of all neighbors y says that x and y are adjacent. And the closed neighborhood of x is nothing but x union open neighborhood of x. Let's see an example. This is the Peterson graph. If you are dealing with 5, we are considering the vertex 5. The open neighborhood of 5 is nothing but the set of all blue vertices. And the closed neighborhood of 5 is nothing but all these pink vertices. I mean, that vertex union the set of open neighborhood. That's it. Now, this was the case when there is a single vertex. What happens if there are some vertices, that is a number of vertices as subset of V? Open neighborhood of S is trivially the neighbors of vertices in S, and closed neighborhood of S is nothing but open neighborhood of S union S. One simple example again, Peterson graph. S is 1, 6, and 8, the blue set of vertices. Whenever we are dealing with 1, 6, and 8, the open neighborhood of S are its neighbors. That means neighbors of 1, 2, 3, and 9. Neighbors of 6, 2 again, 10 and 7. And neighbors of 8, they are 3, 1, and 9. All those neighbors are marked in another color, that is pink. So open neighborhood of S is given in pink color. And if we are dealing with the closed neighborhood, we have to note that 1, 6, 8 are also included in this union. Now, attack and defense on a particular vertex. If you're considering a single vertex X, the attackers of X are n of X minus S. And the defenders of X are n of X intersection S. For example, consider this particular vertex. I have taken S as 2, 6, and 4, the pink vertices. So who are the attackers of 2? Who can be the attackers of 2? N of 2, I mean the close neighborhood of 2, intersection S will be the defenders, and close neighborhood of 2 minus S will be the attackers. So if you are considering 2, its defenders will be 2 and 6, and its attackers will be 1 and 3. So that was a case when there is attack or defense happening at a particular vertex or a singleton vertex. So the same case is extended to a number of vertices. That means if you are considering S to be S1, S2, etc., Sk, and attack on S is any K mutually disjoint sets A1, A2, etc., Ak, for which Ai is a subset of N of Si minus S. Again, let's see an example. You please consider this vertex blue, I mean the set of all blue vertices, that means A and C as S. Then close neighborhood of S is nothing but A, B, C, D, and E. Then any attack is a subset of, I mean A and C. So close neighborhood of A minus S, that means attack can be from B or E. Close neighborhood of N of C minus S, that means attack can be again from B or D. That means attack can be from B, D, or E. And defense will be definitely given by these blue vertices only. Same thing, I mean defense I have already mentioned. Again, defense on S is any K mutually disjoint sets D1, D2, etc., Dk, for which Di is a subset of close neighborhood of Si intersection S. Attack was close neighborhood of Si minus S, whereas defense is close neighborhood of Si intersection S. One more example, if you're considering S to be A, C, and E, the attack is from the outside ones. That means not from the blue ones, but the defense will be given by the blue vertices only. But this vertex cannot be defended by this vertex because it is not a neighborhood. I mean, it is not a neighbor of that particular vertex. So defense is given like this: N of A intersection S, close neighborhood of N of A, intersection S is, that means A or E, close neighborhood of N of C intersection S, that is C alone, and close neighborhood of or N of E intersection S, that is again by these two vertices. So this is the meaning of attack and defense. Actually, the study of alliances in graphs was first investigated by Kritya Sen, motivated by the alliance of nations in war for mutual support. In that paper, actually, the reference is given as footnote in the Journal of Combinatorial Mathematical Computation. Defensive alliance, in the meaning of alliance in graphs, they were concentrated on defensive alliances, and they have defined the defensive alliance like this: a subset of B is a defensive alliance if cardinality of N of X intersection is greater than or equal to N of X close neighborhood of X minus S for every X belongs to S. The vertices of N of X minus S are attackers of X, and those of N of X intersection S are defenders of X. In the case of defensive alliance also, they have concentrated only on a single vertex. But Brigham generalized this concept and named it as secure set. So in this paper, this is the first paper that appeared in the Security in Graphs, the definition as such. Here, alliances are formed so that any attack on the entire alliance or any subset of the alliance can be defended. That means a set is said to be secure if for any subset X of S, any attack on X can be defended by its vertices. So let's see an example. That means this condition, N of X intersection S is greater than or equal to N of X minus S for every X subset of S. By N of X, what we mean is the close neighborhood of X. Here X is not a singleton vertex. X can be any proper subset of S. So if this security condition is satisfied, then S can be called as the secure set. So clearly, if you're considering all the vertices in a graph, that will be a secure set, no doubt. So there is meaning in considering the minimal secure dominating set. Minimal secure set that is known as the security number and is denoted as S of G. Let's see an example. Consider C5. The question is, we want to have the minimal security number or minimal secure set. So the question is whether any singleton vertex can be a secure set here. Let's see. So if you're taking S to be 1, close neighborhood of 1 is nothing but these green vertices, that is 2 and 5. So naturally, close neighborhood of 1 intersection S is nothing but 1 alone. And close neighborhood of 1 minus S is the set of green vertices, that means 2 and 5. So N of 1 intersection S has cardinality 1 and N of 1 minus S has cardinality 2. So the security condition cannot be satisfied here, or in other words, this is not a secure set. So in C5, a singleton set cannot be a secure set because we have considered the set, the vertex 1, and we have seen clearly that it cannot be a secure set. The case is similar to other vertices also. We don't have to take other cases. So a singleton vertex cannot be a secure set. So the next possible number is 2. Let's see whether it is possible. If you're taking S is equal to 1, 2, the close neighborhood of N of 1, 2 is these 4 vertices, 1, 5, 3, and 2. So N of X intersection S, if we are taking X to be S, we have clearly mentioned that a set will be secured if any proper subset of it is also secure. The security condition must be satisfied not only for us, but also for any subset of it. So some cases have to be mentioned. If X is equal to S, then cardinality of N of X intersection S, that is 1, 2, and cardinality of N of X minus S, the outsiders, they are 3 and 5. Cardinality is again 2. So this cardinality is same as this cardinality. That means the security condition is satisfied here. When X is equal to S. No, we are not done. We have to consider the case when X is a proper subset of S. If X is a proper subset of S, you please consider X as singleton 1. So when N of 1 intersection S, close neighborhood of 1 is again 1, 2. So N of 1 intersection S will be again 1, 2. And close neighborhood of 1 minus S will be 5 alone. That means its cardinality is 1. So defenders 2 in number, attackers 1 in number. Defenders number is greater. So security condition is again satisfied. Similarly, if you are taking X is equal to singleton 2, then also the security condition will be satisfied. Or simply, this set 1, 2 will be a secure set in C5. So C5 is a special structure. The structure is same for any cycles. This idea can be extended to any cycles. So can we conclude the security number of cycles? In the case of C5, we have noted that singleton set cannot be a secure set, and a set of cardinality 2, the adjacent vertices, if you are considering 2 adjacent vertices in a cycle, that will be a secure set. So in any cycle, security number will be equal to 2. By the same thing, we can easily explain this. And in the first paper itself, security conditions, when will be secure number equal to 1, when will be secure number equal to 2, and when will be secure number is equal to 3 is clearly mentioned. The first one is a rather simple observation. S of G is equal to 1 if and only if del G stands for the minimum degree in that graph, is less than or equal to 1. Because S of G is equal to 1 means there can be at most one attacker. That means minimum degree is less than or equal to 1. Actually, less than 1 is not of interest because the graph will become disconnected. S of G is equal to 2 if and only if minimum degree must be greater than or equal to 2, and G has a set U comma V where U and V are adjacent, and the boundary of S must be of cardinality less than or equal to 2. Why we are concentrating on the boundary? because of the definition of security number. And security number S of G will be equal to 3. The first two conditions should not be satisfied, and there must exist 3 vertices U, V, and W, where this boundary, the meaning of boundary is something related to the defenders, the N of S minus S. So the number of number of defenders of S must be less than or equal to 3, and the subgraph induced by S must be either a K3 or P3, and if it is a P3, these two conditions, one of the two conditions must be satisfied. This is also clearly explained in this paper by Brigham and others. Now, some lower bounds and upper bounds of S of G can be seen in various papers. Some results are mentioning here. Let G be a graph with minimum degree delta, and then S of G is greater than or equal to ceiling delta plus 1 by 2. Let G is equal to VE be a graph with minimum degree delta, then S of G, this limit, the bound is attained if and only if there is a subset S of V such that S induces a complete graph with ceiling delta plus 1 by 2 vertices and cardinality of N of S minus S less than or equal to the same value, ceiling delta plus 1 by 2. If G is a triangle free graph, then S of G is greater than or equal to 2 times ceiling delta of G minus 1 by 2. Now some upper bounds of S. Let G be a graph of order N and minimum degree delta, then S of G is less than or equal to N minus ceiling delta by 2. Let G be a bipartite graph of order N and minimum degree delta, then S of G is less than or equal to N minus delta. In general, let G be a graph of order N with minimum degree delta and a vertex connectivity kappa. Vertex connectivity means it is a minimum number of vertices whose removal makes the graph disconnected. And if kappa is less than or equal to minimum degree divided by 2 ceiling, then S of G is less than or equal to floor N minus 2 ceiling delta by 2 plus kappa the whole divided by 2. Let G be a graph of order N, minimum degree delta, and edge connectivity kappa 1. If kappa 1 is less than delta, then S of G, another upper bound is given. So many lower bounds and upper bounds are known for security number. Now let's move on to the next definition that we require in this, that is dominating set. A vertex in any graph dominates itself and its neighbors. And if you're considering a particular set of vertices and its close neighborhood is the whole vertex set, then we can say that this is a dominating set. For example, P6, if you're considering P6, the set of blue vertices is a dominating set. The set of all pink vertices is a dominating set, because if you are taking the blue vertices 1, 3, and 5, 1 dominates 1 and 2, 3 dominates 2, 3, and 4, 5 dominates 4, 5, and 6, or in other words, 1, 3, 5 altogether dominates the whole vertex set of P6, and it is clearly a dominating set. Now, a set is said to be secure domination number, secure dominating, if it has two properties. One is it must be a secure set, and secondly, it must be a dominating set. If two properties are satisfied, we can call that set as a secure dominating set. And the minimum cardinality of a secure dominating set is known as secure domination number, because in any graph, if we are considering the whole vertex set, that will be clearly a secure dominating set. So there is meaning in considering the minimum secure dominating set, and that is denoted as gamma ST. Again, let's see an example. Consider P6. In the earlier example, we have seen a dominating set only, but here we require one more property. It should not, it must be dominating as well as secure. So you please consider the set of all blue vertices here. Clearly it dominates P6, no doubt, because 2 dominates 1, 2, and 3. 3 dominates 2, 3, and 4. 6 dominates 5 and 6, and hence the set of all blue vertices dominate the whole graph. No doubt. Whether it is secure. Is it secure? If you are considering the whole set 2, 3, and 6, yes, clearly it is secure because defenders are 2, 3, and 6, and attackers are 3 in number. 1, 4, and 5 can be attackers. So defenders 3, attackers 3. Condition is satisfied. Now, if you're considering any subset of these blue vertices, then also the number of defenders will be greater than or equal to number of attackers, or in other words, this is clearly a secure set. A basic result in secure domination number of a graph is this: gamma SG is greater than or equal to cardinality of vertex set of G by 2. It is a very simple result actually. Suppose that S is a secure dominating set in G. Then for any proper subset of S, the security condition must be satisfied. We can think about the whole vertex set S also. So if X is equal to S, then the security condition is satisfied. That means N of X intersection S, in the place of X, we have substituted S greater than or equal to N of S minus S. Again, in the place of X, we have substituted S. So here, since S is a dominating set, N of S will be is equal to G. I mean, the whole vertex set of G. So you can apply like this. N of S intersection S will be called S itself. And N of S minus S will be V of G minus S. But just apply the modulus property. Modulus of V of G minus S is greater than or equal to mod V of G minus mod S. So you will get simply mod S is greater than or equal to cardinality of V of G by 2. So in any graph, this secure dominating set has a particular property. This set will be at least N by 2 vertices. So consider Pn again. I mean, we have seen in P6, this was a secure dominating set. The set of all red vertices constitute a secure dominating set in P6. The idea is similar in any paths. If you're considering P9, consider those red vertices. It has a pattern now. So we can generalize the result in any paths. That means secure domination number of Pn is, as we can expect, that will be nothing but ceiling n by 2. We have seen earlier that secure domination number is at least ceiling n by 2. In the case of paths, it says ceiling n by 2 itself. What is secure domination number of the Peterson graph? Because it is the smallest structure that comes to our mind whenever we are studying something. So this is the answer. If you're considering these 5 vertices, I mean the red vertices, that will be clearly dominating as well as secure, or in other words, secure domination number of Peterson graph is 5. In this paper, we can see some simple results like this: secure domination number of path, secure domination number of complete graphs, secure domination number of complete bipartite graph, and they have also proved that for many common graphs such as paths, more cycles, complete multipartite graphs, N cubes. It is a beautiful network, the hypercubes, Peterson graph, and many more. Gamma SG is equal to ceiling n by 2. Why we have used the word more cycle is just because of this. When n is equal to 6, 10, etc., secure domination number of cycles is cardinality of n by 2 plus 1. For all other values, it is just ceiling n by 2. For these particular values, this will be ceiling n by 2 plus 1. Now, in the case of many well-known graph products, such as Cartesian product, lexicographic product, and strong product, the secure domination number have been studied. And I have quoted some results in the Cartesian product. It was a paper that appeared in a KCE journal in the year 2017, and it was by Barnett and et.al. The result is like this: secure domination number of PM, Cartesian Pn is cardinality, I mean ceiling Mn by 2. That means that bound is attained here also. That is a beautiful proof. You can just refer that paper. If we are taking the Cartesian product of paths and cycles, again similar results occur. That is sealing Mn by 2, except possibly in the cases M is identically equal to 3 mod 4, M greater than or equal to 7. When N is equal to 2 mod 4 and M is identically equal to 1 mod 4. For these particular values, this bound is attained. Again from the same paper, secure domination number of Cm Cartesian Cn. Actually, Pm Cartesian Pn is known as the grids that has an important role in the networks. This is Cm Cartesian Cn is known as the torus. That is also a very good network, and hence these studies are important. This big result actually, this is the one. In general, for any two finite simple graphs G and H, secure domination number of G and H is less than or equal to gamma Sg into cardinality of V of H. Only a bound is attained. Definitely a bound can be attained because we don't know any properties of G and H. This is again from the same paper. Now, let's see some graph operators. The security number and secure domination number in some graph operators. And one such graph operator that we were interested was double graph defined by Munarni and et.al. in discrete mathematics, appeared in 2008. The double graph of a simple graph G was defined like this. V of G is equal to U1, U2, etc. Un. Then in the case of double graph, we will have a copy of the vertices and I will show you an example so that the idea will be clear. This is the original graph G. In the case of double graph, we can see two copies of the original graph. This is the original graph. We can see two copies of the original graph. Simply copies. Whole vertex set and whole edge set is there. Moreover, if 1, 2 is an edge in the original graph, 1, 1, 1, 2, 2 will be adjacent, 2, 1, 1, 2 will be adjacent. Something like X. So corresponding to an edge, an X will be formed in the case of double graphs. That is the structure of double graph. This was defined by Munarni and others. So this is one of our papers that appeared very recently in Indian Journal of Pure and Applied Mathematics. In that we have shown that security number of double graph is less than or equal to n, and secure domination number of double graph is equal to n. In the same paper, we have studied the corona structure, security number and secure domination number of the corona structure. The corona G corona H of two graphs G and H is obtained by taking one copy of G and cardinality of V of G copies of H. Moreover, join each vertex of the ith copy of H to the ith vertex of G for all vertices. Moreover, that means if V of G is equal to U1, U2, etc., Un1, and V of H is equal to V1, V2, etc., Vn2, then V of G corona H is U1, U2, etc., Un1. That means a copy of G and cardinality of V of G copies of H. They are marked like this as a product. The example will be easier. If G is equal to C5, we can see the C5 that is there, and H is equal to P3. P3 is added to each vertex of C5. This is the corona structure. So in the case of corona also, we have obtained the security number of G corona H as a bound. For any two connected graphs G and H, S of G corona H is less than or equal to N2. This is our paper that appeared very recently. And one more bound is attained. If some conditions are imposed on G and H, we get a better bound, that is S of G corona H is less than or equal to S of H. Now another graph operator, again one more, S of G corona, secure domination number of G corona H. Earlier we have studied the security number of G corona H, and secure domination number of G corona H is also obtained in the same paper. If G is equal to N1 M1 and H is equal to N2 M2 with gamma S of H is equal to ceiling N2 by 2, then gamma S of G corona H is less than or equal to n1 into ceiling 1 plus n2 by 2. A good bound is attained in the case of corona of graphs. Like earlier, if some good conditions are imposed, we get a better bound. Secure domination number of G corona H is less than or equal to n1 into ceiling n2 by 2. That means if G is equal to n1 m1 and H is equal to n2 m2 with gamma S of H is equal to ceiling n2 by 2, then where n2 is odd, this is one condition that is required, and cardinality of nh of x intersection S is greater than cardinality of nhx minus S for any x subset of S, we will get this bound. So we have studied double graph. I mean, these are some well-known graph operators. Double graph, corona of two graphs. Now let's move on to Michelskian and generalized Michelskian. The Michelskian graph is defined like this. For a graph G is equal to VE. The Michelskian of G, mu of G is the graph with the vertex at B of mu of G as B union B dash union a singleton vertex Z, where B dash is a copy of V itself, and the edge set of mu of G is equal to the edge set in the original graph union U B dash and union B dash Z. I'll show you an example. If you're considering P6, the blue vertices, this is the original graph G, P6. Its Michelskian means one copy of these 6 vertices, that means that is green in color, and a single vertex that is adjacent to all these new set of vertices. So the original graph is there as such, new copy of vertices, and the singleton vertex which is adjacent to all those vertices that are newly added. Moreover, if 1, 2 is an edge, again there will be an X, but this is different from the double graph. So 1, 2 dash and 2, 1 dash. This is the meaning of Michelskian graph. The same concept can be generalized. That means these layers can be increased. That is known as the generalized Michelskian. I mean, the concept is same as this. Earlier, we have considered P6 and only one copy of the vertex set. Here, there are 3 copies of the vertex set. So this is known as mu3 of P6. I mean, 3 layers of P6 are there. I mean, the vertex set only, not the edge set. P6 is there as such, and 3 copies of the vertices are there. And one newly added vertex will be there, that is added to, I mean, that is joined to the last set of 6 vertices. So this is the meaning of generalized Michelskian. This can be applied to any graph actually. So in the case of generalized Michelskian also, we have obtained the security number and secure domination number. This is like this. Security of mu mg is less than or equal to n. Security number of mu mg is less than or equal to n. That is generalized Michelskian with m layers of the graph is less than or equal to n. Actually, we have to take that just the copy of G. The condition will be satisfied. And the security number, secure domination number of mu of G is equal to n plus 1. In the case of security number, we could attain only the bound, because without knowing the property of G, we can't attain a good equality. But in the case of secure domination number, we have attained equality. Secure domination number of mu of G is equal to n plus 1. Again, this is also a result that appeared in our paper recently. And this is a lower bound and upper bound for the secure domination number of mu mg, that is cardinality of n into m plus 1 by 2 less than or equal to gamma s of mu mg less than or equal to n into ceiling m plus 1 by 2 plus n. Then another network, that is honeycomb network, that is a beautiful network actually. HC, actually a new network will be constrained. I mean, honeycomb network are inductively constructed. For example, HC of 1 is nothing but the hexagon. HC of 2 means we will add hexagon to its boundary. So HC of n can be attained from HC of n minus 1 by adding hexagons on its boundary. Let's see an example. Look at here. HC of 1 is just a hexagon. HC of 2 means hexagons are added to the boundary. Then to this particular graph, hexagons are added to the boundary and we are obtaining HC of 3. And to its boundary, we are adding again hexagons so that we will obtain HC of 4. And we can construct the next set. That means HC of n can be constructed from HC of n minus 1 by adding hexagons on its boundary. So, in our paper that appeared in JOCO in the year 2020, we have obtained the security number and secure domination number of these honeycomb networks. We have the honeycomb networks. It is clear that the number of vertices is 6n square and the number of edges is 9n square minus 3n. That is clear from its structure. So security number of honeycomb network of stage n is nothing but 2. And secure domination number of HC of n is less than or equal to 3n square plus 1. We'll show you the outline of that proof. Secure domination number of HC of 3, they are marked in red colors actually. This concept is generalized in the case of HC of n, and we have obtained the result that secure domination number of HC of n is less than or equal to 3n square plus 1. Now another network is Sierpinski graph. It is again a well-studied class of graphs. Sierpinski graph is a beautiful structure and it's a very beautiful network also. The Sierpinski graph of dimension t denoted by S of k and t. Some call this as generalized, this is Sierpinski graph. Generalized Sierpinski graph is something different. In the place of kn, if we are taking any graph, that can be called as generalized Sierpinski graph. But I'm just mentioning about Sierpinski graphs only. So S of k and t, where t greater than or equal to 1, is the graph with vertex set as the set of t tuples of 1 to etc. n, and the edge set is defined as follows. 2 vertices, 2 t tuples are taken because they are the vertices, I1, I2, etc. it, and J1, J2, etc. jt are adjacent if and only if there exists some h belongs to 1 to etc. t such that ik is equal to jk for all k less than h, ih is not is equal to jh, ik is equal to jh, and jk is equal to ih for all k greater than h. If these conditions are satisfied, the edges will be there. And S of K3T is nothing but the Hanoi graphs, the celebrated Hanoi graphs. Hanoi graphs, as some of you know very well, that it is obtained from the Tower of Hanoi problem. So in the place of Kn, if we are placing K3, we will get Hanoi graphs. But we have shown is S of K4-3. Look at here, please. K4, this is K4. So if you are considering this part only, that is S of K4-2. This is S of K4-3. And if this copy is placed in the place of K4s, we will get S of K4-4, and it can be generalized like that. Any big structure can be obtained from the previous structure. That is similarly as in the honeycomb networks also. So this is also an inductive definition, and these two are some classic papers in in the case of Sierpinski graph. One is by Sandy Closer and U. Milinov that appeared in Czechoslovak Math Journal, and the another one was by Hinz, Sandy Closer, and Semslik. That is a survey and classification of Sierpinski graph types that appeared in DAM in the year 2017. Actually, this survey helped us a lot to understand the Sierpinski structure and its properties. Actually, we have studied security number and secure domination number in the case of Sierpinski structure also, but that is not yet published. It is in the final stage. Final remarks are coming to us. So I'm not going into the details of the results obtained in the case of Sierpinski graph, but that is also studied. These are the main references. I've shown the references in the respective slides itself. Still, I'm showing you the many main references.
Let's thank the speaker. And I'll stop the recording.